All right. So the objective in this lesson is to solve trigonometric equations. Good job on that objective, Edmentum. Good job. um, oh, and they don't even fill it out for you on the guided notes. They still expect you to fill that part out. All right, so we're gonna be. They give you actually quite a bit of resources here on the guided notes. So this is something I do recommend you guys print out when you're taking your mastery tests, and to just have like a bunch of these when you're taking your post tests. So this is another resource you guys can use with the guided notes. And that's just literally going into this little folder right here. All right, so let's do the introduction. So we're going to be using different functions like this in the real world. So techniques of doing this, like terms is definitely one of them. So remember, if it's a like term, the trig function has to be the same and the angle has to be the same. And any powers will have to be the same as well. So they're just doing a quick review on like terms. And eliminating radicals is another way of doing this. So this is just a matter of squaring both sides. In order to get rid of a radical, we have to square both sides. Again, this guy should be all review from your algebra and algebra 2, hopefully. Taking the square roots. So when we take the square roots, this is helpful when we're trying to find, for example, our zeros. So if we have this function, this helps us find the zeros. So we can see here it's not exactly -1, and this one isn't exactly 1. So this is a good way of solving this. It's close because think about it. The square root of 4 would be 2, which would make it 1 and -1. So that's why we see it a little off here. So it looks like the first bit is literally just going over things that we should know. Factoring, I think if you guys have come to me for tutoring or anything, you guys know that my favorite way of factoring is the box method. So whenever we're doing this, we're going to want to put the x squared here, the -5 here, and we want this is kind of like our little goal. This is the goal. We want to make these two equal. So x times x gives us that. And then if we do -5 times +1, this will give us that -4. So that's how we get these two. I usually use the box method because even if you have an A, the box method's really good. And if you mess up, the beautiful part about the box method is you can just be like, I'm gonna try other numbers. There's the X method too, which is good, but it gets a little trickier when you have an A. Then you should be factoring by grouping because that means you have a really long polynomial if you have an F. I do know. All right, so let's do some reviews on quadratics. When are we gonna get to trigonometric functions here, Edmentum? What's going on? Not that I'm complaining. So if we're solving this, what I recommend doing is box methoding this. So we're going to put an x squared here, a 2 here. The 3x's are kind of reminder. X, 2 and 1 gives us 2. So 2 times 1 gives us 2. 2 times x gives us 2x. 1 times x gives us x. And these do add up to make a +3. So that's our work for this. So this is going to end up being parentheses x plus 2 parentheses x plus 1 parentheses equals 0. This causes them to split up into two equations. So the whole reason of doing this is what's called the zero product property. If you make x plus 2 equals 0, it doesn't matter what x plus 1 is. 0 times anything is 0. And we're also going to do x plus 1 equals 0. So our answers become x equals negative 2. And our other answer is x equals negative 1. So that's how we solve this by factoring. This one, we could use the box method, but I'm not sure how familiar you guys are with your equations. I'll do it by the box method. Okay. So this one is known as dose. There is no game called dose. There is a game called Uno. So this comes from the idea of a squared minus b squared is equal to a plus b, a minus b. So if we're looking at this, our a squared is x squared. So our a is equal to x. And our b squared is 49. Therefore, our b is equal to 7. So when we factor this out, we should get this x plus 7 times x minus 7. And let's say you guys don't remember this formula, which is fine. A lot of people don't. I usually remember it every time I have to teach it. Um, you can do it this way. And you have a 0 here. So if you're doing this, it's x times x, 7 times negative 7, and you'll see that this still works out. These cancel out, so you still get 0. So if all else fails, the box method still works. So again, if you don't remember, if you can't identify that this is dose, the box method should eventually lead you to the answer. You have x plus 7 equals 0. And then you have x minus 7 equals 0. So x equals negative 7. And x equals positive 7. So those are our answers for that one. I wonder if they're going to bring up dose in the example. They don't. They're just like, yeah, solve it. You got this. You know how all we've been making. It's like, you know how all we've been making you do is look at a trig sheet? Now we're going to make you randomly remember how to factor. So let's we put that here. We put a negative 15 here, and we have a 7x here. So this is a good example of when the box method will help us out because there's an a. So this becomes 2x. This is an x. And I'm going to try negative 3 and a positive 5. And luckily this ends up working because 2x times 5 is 10 and negative 3 times x is that. These would add up. So if they do not add up, if this wouldn't have added up, I would just keep trying until I got the right answer. I got lucky. Sometimes we don't get lucky. So when I type this in, I really wish I could move this, but I can't. I get 2x take away 3 times x plus 5. I'm going to set that equal to 0. So that's my equation from up top and from on the side. Is this making sense, guys, how to do the box method? Cool. That's good. So Nick and Garrett, I'm sure you guys were like, why does he keep doing the box method in Algebra 1? But now you see, it's like in every math class we have to do the box method. What? So I add 3 to both sides. Thank you. I add 3 to both sides and I subtract 5. And I already solved for x on one side, but the other one I have to divide. So I get x equals 3 halves. Which if I want to get fancy, I can do the little equation editor, push the little fraction button and go 3 halves. And then there's a fraction. And then they'll show. I like how they like make it seem all simple. It's like, yeah, totally. Like you got this, and then there you go. Yeah. This one, it's not really tricky. It's just a matter of like, hey, it's not equal to 0. Move that over. And that's pretty much all you do. So what we're gonna do here, move this over, plus 18. And then I notice, wait a minute, there's a GCF here. I can literally divide everything by 3. So if I take out a 3, I get x squared minus 5 plus 6. And this is 5x. So what I can do here now is I can do a box method for only x squared and negative 5x plus 6. So this kind of makes this a little easier for me to do. I'm getting this negative 5. My first instinct was to try negative 1 and negative 6, but that would give me negative 7. So I would switch this to doing negative 2 and negative 3. That will still give me a plus 3, but when I multiply everything out, it's going to give me that negative 5x that I want. So then my answer, well, not even my answer, I still need to kind of show my work. So I have to do x minus 2, parentheses, x minus 3. All of this is equal to 0. I guess I could have technically showed this step, but whatever. And then I'm going to solve this into two different problems. So x minus 2 equals 0. X minus 3 equals 0. So we get x equals 2. And x equals 3. So notice how this a didn't really affect anything because we're solving for zeros. We're solving for when it crosses the x-axis. If this is skinnier or fatter, it's not going to change where it crosses the x-axis. No, it's just literally just loop, or it could be loop and it would still have the same x and y's. It's not necessarily easier or harder, it just determines the graph, but it doesn't really affect our x and y's. And then this part's going to be interesting, hearing if you guys remember how to do the box method and stuff like that for the self-evaluation. Don't just blow through it, guys. Like, kind of think about it. That way you reflect on it. Reflecting on it is a really good way of knowing where you're at and what you need to improve. That's good. All right, so what? All right, guys. So we're still solving regular equations. So this looks simple. We might be able to do a fun Kahoot after this class. So I'm going to subtract by 5. So I want to subtract both sides by 5 first. So subtract both sides by 5. Next thing I want to, before I get to this radical, I have to get rid of this 3. So I'm going to divide both sides by 3. Nice and simple. Then I want to get rid of this radical. So in order to get rid of a radical, you have to square both sides. All right. Now I'm going to need to move this 9 over. Once I move that 9 over, I can start doing the box method or whatever to solve it. So I'm going to subtract 9 from both sides. Now it's a nice quadratic. So you can either factor it or use the quadratic formula. They want us to factor. So if you box method this, you need a negative 9. So I'm going to x method this for those of you who might be more familiar with the x method. You want to get a negative 8 by adding and a negative 9 by multiplying. So what I would do is I would do negative 9 times positive 1. If you add these two together, you get negative 8, but if you multiply them, you get negative 9. So this means you need a positive 1 and a negative 9. So it has to be this one. Right? And then from there, you're going to split these up into 2 equations. So one of them has to be positive 9 and one of them has to be negative 1. It says solve by substituting, but I always split them up into 2 equations. I think it makes it easier than just substituting. What's up? Okay. I have not been to Costco. Yes. I'll try it out next time I'm at Costco. All right, guys. So the next thing we're going to solve for, guys, is this idea of trig functions. So here's the trig functions in the trig functions unit. This is so x is an angle and 1/2 is the fraction. So remember, trig always comes down to triangles. So if you're ever stuck, just remember that all trig is are triangles in the unit circle. So sine is opposite over hypotenuse. And the thing with this is we're solving for a y value. So if you look here, there's going to be repetitions. It's going to keep repeating over and over so many times. So that's how come there could be a bunch of answers for this. It depends kind of on the period. So we're going to talk about how period, I'm sure you guys kind of dealt with it a little bit in Algebra 2. There's a phase shift, meaning that you can move this over. These two are the same, it's just moved over a little bit. And we're going to talk about how that affects our answers. And then tangents, a little similar. Tangent has asymptotes. So tangent goes like this, but it can never get to pi over 2. So if you ever look at tangent of pi over 2, tangent, give me a second, let me write this. Tangent is opposite over adjacent, right? TOA, it's the TOA. So opposite over adjacent is kind of the same thing as saying sine over cosine. The reason for this is we have opposite over hypotenuse over adjacent over hypotenuse. Well, since we're dividing a fraction, it would be opposite over hypotenuse times hypotenuse over adjacent. You flip it and then multiply it. So that's why tangent is the same thing as sine. So if our cosine is 0, then we're going to get undefined. So that's what come at pi over 2, our tangent never touches the line. So that's the reason why it kind of repeats like this instead of repeating in a wave like cosine and sine. Does that make sense, guys? Oh, sine over cosine, sorry. And then trig function, the unit circle is the best way to do our trig functions. So if we're doing our trig functions, it's always good to use the unit circle. Always remember that sine. I know we've, I know when we do sine, sine is equal to y. It's okay. And then cosine, I should use theta. So sine is our y and cosine of theta is our x. So that means tangent theta is going to be our y over x. So that's a good way to kind of use the unit circle here. So that's why the unit circle is so important, is because we can use it to basically find these cosine and sine values a lot easier. And the reason why it works that way is because in a unit circle, the hypotenuse is always 1. That's why it's a unit. It's 1 unit as the hypotenuse. All right. So collecting like terms. So for example, in this case, when we're talking about like terms, if we're looking at cosine, for example, if we look at this and this down here, we'll see that the x values are the same, meaning the cosine is the same. And I forgot that when I scroll down, the line moves too. But you'll see that this is 1/2 and this is also 1/2, meaning the cosine of 5 pi over 3 is the exact same as pi over 3. So that's a good way of seeing those repeating terms on the unit circle as well. And you can do that with cosine as well if you're squaring stuff. So this, we use the same steps. And once we find all the steps, we just use our unit circle to solve for it. And factoring. So let's see when we were factor. So in this case, we're going to pretend that this is sine squared. So we're going to pretend that our u, this is called u substitution. We're going to say u is sine of x. So then this equation right here would be 2u squared minus 3u plus 1. They call it u substitution, but you can really do anything with this. I remember when I took Precalculus, I was always using u's, but you can easily just use that. The only thing you have to do is after you get to this point, just remember to substitute it in, and then you use your unit circle to solve for it. So that's how come we've been reviewing how to do factoring, because if we use u substitution, we'll have to start factoring. And then they're showing. He's scared his brother thinks it's really cold. And then, so that's just, this is just another example of doing it and then using the unit circle there. And then if you need to solve using square roots, you can use them also. So you're kind of just substituting things in to make this a little easier. And you can use your Pythagorean identities to solve things too. So remember that the Pythagorean identities is this idea of x squared plus y squared equals 1 squared. So that's another way of saying cosine squared plus sine squared equals 1, which is again the same thing as saying cosine squared is equal to 1 minus sine squared. x. So we're kind of bringing all of these together. If you guys don't want to like write all this down to the point where you understand, to the point where you have all these formulas, it's all on this sheet actually. I think it's, where is it? Pythagorean identities. So there's this here. You can rewrite this to be 1 minus cosine. So these are good little examples of the Pythagorean identities. If you need them, you can just manipulate it to kind of help you out here. So once we start getting to solving these equations, there's going to be a lot of substitution, and there's going to be a lot of looking at the formula, seeing if we can simplify it into easier angles. So, for example, if we're adding two angles that aren't on the unit circle, you can try using some of these formulas to try to change it into angles that are on the unit circle. All right, let's get, I at least want to get to an activity. Okay, so here's a problem here. Do I have it automatically on the answers? I didn't want the answers. Why did it answer it for me? Okay. So, one thing we can do when we're solving this, we want to solve this in terms of cosine. So, if we want to solve this in terms of cosine, we have this sine. So, we can replace that sine squared. So, sine squared x is the same thing as saying 1 minus cosine squared x. So I'm going to substitute it in here. So this becomes 1 minus cosine squared x plus 3 cosine x minus 3. I'm going to distribute this 2, and I get 2 minus 2 cosine x squared. Uh, Oh, I was like, what else do I distribute? But obviously, I just write the rest down. I can simplify that 2 and this 3, so this becomes 2, negative 2, cosine squared x plus 3 cosine x minus 1. So from here, I can use u substitution. I'll use y substitution because I feel like it. 2y squared plus 3y is, or minus 1. I don't really like this negative, so I'm just going to change all the signs. By changing all the signs, I don't really change much. Like, I'm basically just saying instead of this parabola, I'm going to be dealing with this parabola, but my zeros would still be the same. So by flipping it over, it doesn't really change your, it doesn't change your factoring. So when you're solving for this, you're going to change this to be, do a box method here. 2y squared, 1. So if I do this, I could do negative 1 times negative 1. This is a 2, and this is a 2y. This is negative 2y. This is negative y. And it would give me my negative 3y here. So I end up getting this as, and remember what y was? Y represented cosine of x. So 2 cosine of x minus 1. I don't know how picky Edmentum's going to be with this. And that's going to be cosine of x minus 1. Oops, minus 1. I honestly forgot what the answer was already, and it showed it. So if I do this, I'm just gonna do it again and see, unless it wanted me to solve for this. If it wanted me to solve for this, for the actual answers, it would be, oh, I wonder if because I put cox instead of cos x. Oh, no, 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 no. Control Z. Control C. All right, let's see what it wanted for the answer. Oh my gosh, it literally just wanted me to substitute. It just wanted me to substitute the sine squared x. That was it. So I did a little bit more work than I had to, but we can see how we can solve these equations afterwards. All right, so now we're gonna rewrite this one. Nope, I don't want to see it. I don't want to see it. Clear it. Clear it. All right, so I'm going to try to make these in terms of it wants it in terms of tangent. So seeing how this is a secant squared, I'm probably going to want to look at my Pythagorean theorems because I know my Pythagorean theorems have all that square stuff. Then I see here that secant squared is equal to tangent squared plus 1. So I can just substitute that in. So I'm going to get this 2 tangent squared x plus 1 plus tangent squared x minus 3. Distribute this out. I get 2 tangent squared x plus 2 plus tangent squared x minus 3. Because the exponent and the trig function are the same, these are like terms. So my answer ends up being, and there's a 2, and there's a 1 in front, invisible 1 in front of here. So we get 3 tangent squared, control up for the squared command, x. This is a 2 minus 3, so that should be a plus 1. So if I did this right, if I did this the way, oh wait, that's a negative 1. So this should be a minus 1. Minus 1. The only thing I can think of, oh wait, no, it wants it in terms of tangent x. So what I'm thinking they might want me to do is might want me to factor out a tangent here, but let's see what Edmentum wanted. Okay, so they were fine with this. You have rewritten that as this. That's a typo because that's supposed to be secant, not a sine in terms of tangent. So this is a good way to do this. So now that I kind of understand how they want me to solve it, it makes it a lot easier. Now we want to solve for this in, nope, I don't want to see it. Delete it. Delete it. In terms of cotangent. So if I look at my equations, it has a cosecant squared. So we're probably going to want to use our trig functions. Oh, and that's just 1 plus cotangent squared. So I'm going to rewrite this as 1 plus cotangent squared. So 1 plus cotangent squared x. Oh, and this one's no distributing, no nothing. It's just this 1 turns into a negative 4. So we're going to get cotangent squared x minus 3 cotangent of x. That's not an O. Minus 4. Minus 4. And that should be our answer. Yep. So we rewrote it in terms of cotangents. All right, and then I'll start the unit activity in the next lesson. So that'll be it.